All right, so you've dealt with exponents before. Exponents doesn't mean like a former opponent, right? What is an exponent in a math class? Anybody, you can shout it out. It's a number on top of a number. Okay, that's a good way to start. It's a number that's written to the top right or left of the number? To the top right of the number. And that exponent indicates what about the smaller number that's to the left and lower and bigger? How many times it's multiplied by? Very good. Okay, so that's really what an exponent is. So back in little school, and I refer to that often, whatever grade that was for you, you learned addition, right? 2 plus 2 plus 2. But then you realize that, hey, if you have repeated addition and you have multiple terms, you can abbreviate that process using what operation? Multiplication, right? You could say, oh, I have 3 of those terms. So multiplication is really just abbreviated addition. That's all it is. All right? And then if you had something similar like 2 times 2 times 2, and now you were multiplying, there was a way to abbreviate repetitive multiplication, right? And that was exponentiation. So now you would have 2 to the third power. So exponentiation is nothing more than abbreviated multiplication, just like multiplication is abbreviated addition. So you kind of have this hierarchy of operations, or a ladder, right? Here's the ladder. And on the bottom rung, you have addition and subtraction, right? And then on the next rung, moving up, you have multiplication and division. And then moving up to the top rung for now, you have exponentiation, which takes also the same rung with square roots and cube roots and all that stuff, okay? And there are higher rungs, but these are kind of the 3 rungs. And this is where PEMDAS comes from, right? So PEMDAS kind of follows that same order. All right, so blah, 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 blah. There we go. Yeah. No. If you don't have your iPad yet, I would encourage you to print these notes out somewhere, either in the library or at home. Yeah, until you get your iPad. They're giving out iPads kind of, I don't even know how they're deciding who to get them when. But anyway. All right, so something's going to be of the form b to the nth power. All right? So n is called the exponent. Right? Oh, sometimes you can refer to it as the power. And then b, I use b because b is called the what? Base, right? B-A-S-E, not B-A-S-S, right? Base. All right? And so the exponent n, if n is a positive integer, that is, it tells you how many times you're multiplying the base together. Now, n doesn't have to necessarily be a positive whole number, but to start off today, it will be, okay? So this exponentiation works because we are collecting factors, all right? So the rules of exponents work because they are abbreviated multiplication. So here are some words that are associated, and we need to say them, okay? So factors imply what operation? Multiplication, right? And repeated multiplication then leads to exponents, which again then means that we're combining multiple factors. And I just threw that word in there because it's fun to say. How would y'all pronounce that last one? Worcestershire? Or Worcestershire? Yeah, okay. So the rules of exponents work because exponentiation is abbreviated what? Multiplication. And things that are multiplied together are called what? Factors. So they're all related, right? They're all related. Whereas things that are added or subtracted are called what? Not factors, but terms, okay? Hugely important. Terms are added or subtracted. Factors are multiplied or divided. All right, cool. Let's try example 1. It says to express each expression in the form b to the n such that n. Okay, well, let's see. N is just going to be a variable. That's a variable. And what does this little guy? Y'all seen him before. It's the Greek letter epsilon, but it means is an element or member of. Okay? It's in the group of, and then this symbol here is one of your primary number groups. Okay? You have real numbers, whole numbers, integers, rational numbers. These are the natural numbers. Okay? Natural numbers. Y'all know what the first natural number is? These are sometimes called counting numbers. Kind of the first, most basic set of numbers. 1, yeah, good. It starts with 1. Not 0, but 1. So like back when early cavemen walk around, no thought of 0 in caveman head. Cavemen find rock. Cavemen like, ooh, rock. Cavemen pick up rock, keep walking, ooh, another rock. So now cavemen have rock, rock. Another rock, ooh, rock, rock, rock. Hold on, we need a better counting system. So then natural numbers. 1 rock, 2 rock, 3 rock. Okay. So then all these cavemen started picking up rocks. Those were the natural numbers. They started counting things that they acquired, right? And soon all the rocks were taken, and there was that one caveman who now had how many rocks? He was late to the game. Forget that. He had 0 rocks. So 0 came much, much later. If you add 0 to the natural numbers, and we can write it out like this, just so you know what they are. The natural numbers, you can write it like that. It's going to be the set, so that's a little brace. It starts at 1, 1, comma 2, comma 3. And once you establish the pattern with a minimum of 3, I think you'll know what comes next, right? 4. So you can just put ellipsis points and close it off. So it's an infinite set. It goes on forever and ever and ever. Those are the natural numbers. If you add 0 to that set, you get the whole numbers, okay? And again, once all the rocks are taken, some guy that doesn't have rock want rock, right? So now he has to borrow rock from other cavemen who's the rock magnate. And that's the idea of what type of numbers when you borrow? Negative, right? So if you add the negative natural numbers with 0, you get the set of integers, right? So -3, -2, -1, 0, 1, 2, 3, so on and so forth. Those are the integers, all right? And then you have all these rocks in hand, and you drop one, oop, and rock break. And that's the idea of what? If rock break? Rational numbers, good. Fractions. Fractions are decimals. They represent parts of things. And so those are called the rational or ratio fractions of numbers. And then you have a whole disjoint set called irrational numbers, like square root of 2 and pi, that cannot be expressed as a fraction. And then you combine those together and you have real numbers, okay? So that's the number sets. And you've probably started off every math class with those. All right, so here we go. 5 times 5 times 5 times 5 times 5. We're not interested in coming up with the actual answer. We want to write it in the form b to the n, right? So it's going to be 5, and how many do we have? 6. Okay, perfect. Is that boring? Sorry. Questions on that? Cool. B, oh boy, okay. So that's 1/2 as the base to the second power times 1/2 to the 7th times 1/2 to the what power? To the 1th or first power, yeah. So you can add things there. Feel free to add things to help yourself. And so I know that it's going to end up being 1/2 to the what power? 10th, good. So here's kind of the first rule of exponents that students kind of get confused. Do we add those exponents when the bases are the same, or do we multiply them, or do we what, squish them together? We add them, right. So what you're going to always do is come down one rung on the operational ladder, because we're multiplying here, right? Something times something times something, that's multiplication. What's one rung lower than multiplication? Addition, right. So you're adding them. So these just tell you how many of those bases you're multiplying total, and we have 10 of them, okay? Now that's a fine answer, but let's start thinking about multiple choice questions on a test. This is the same as 1 to the 10th over 2 to the 10th, right? Because there's this property that says a over b to the nth is the same as a to the nth over b to the nth, right? What the property that we just did was like a to the nth, b to the mth power, a is equal to a to the n plus m. So that's the rule that we just used. We added up the exponents. But now you can use this other property of exponents, and you can give each factor the exponent. And of course, 1 to the 10th is 1, so that's the same as 1 over 2 to the 10th. So this is another version of the same answer. All of these are equivalent to each other. And so the beauty of having like a multiple choice question is if you get to this top answer here, I may not have that as an answer choice. I may kind of force you to do a little bit more and get down to something like the bottom and have that as an answer choice, okay? So that's kind of what multiple choice questions are. So as you're working through your worksheet, kind of think at the end like, oh, what else could I do with this? How can I manipulate it to be equivalent but look a little bit different, all right? All right, so now that you've seen that, go ahead and take about a minute and see how far you can get on this one. We reviewed the rules and notice that we have increased the level of fun really quickly here from A to B to now C. Oof. Okay, go. Don't feel like you have to eat the elephant in one entire bite, right? You'll choke on the elephant. You eat an elephant one tiny bite at a time. So inch by inch, it's a cinch. Do something per line, maybe to each factor, and it may take you 10 lines working down to get to your final answer, but you'll eventually get there. These negatives make it a whole lot more interesting. Remember, those rules of exponents only work if your bases are the same. If they are not the same, they only even differ by a negative sign, those rules don't work. Okay, so if you're not done yet, that's fine. I'm going to kind of take inventory here. I have 1, 2, kind of 3 main parts of this problem. Let's focus on the first one. What exactly am I raising to the 4th power there? Is it 3.1 or negative 3.1? It's just 3.1. Very good. All right. You should always say what you mean and mean what you say. If you use the order of operations, negative 3.1 to the 4th is the same as negative 1 times 3.1 to the 4th power. Okay? If you intended it to be the negative 3.1 to the 4th power, it would have to be this, negative 3.1 to the 4th power. Okay? And they're not. They're different. All right? So parentheses are very, very important. Now, just to kind of take note, what would happen if you raise any negative number to an even power, like squared, 4, 6, or whatever? What happens to that negative? It becomes positive, right? Because you're pairing them up, and a negative times a negative is a positive. So any negative number raised to an even power is just going to be the positive version of that number raised to an even power. Whereas, just since we're right here, if I have negative 3.1 to the, let's just say, 5th, okay, what happens if you have a negative number raised to an odd power? It stays negative. So that can be written as negative 3.1 to the 5th without parentheses. Okay? And the reason that works is because, remember, that is negative 1 times 3.1 to the 5th. So this is very important for you to understand early on when you're writing your work down, when you're typing it into a calculator eventually. If you miss grouping symbols and you tell it to do something that you don't intend, it's going to interpret it differently, okay? So doing this off to the side, showing y'all, this is what I will eventually or always call bench work. So you could think of the problem as being like the project. And we want to kind of work straight down and not interrupt the flow of the project. But if we have to go off to the side to do like long division or multiply, that's exactly where we do it, off to the side on our workbench, okay? And then we bring it back into the project. So that first term is still going to be just negative 1, and you could do that to help yourself, times positive 3.1 to the 4th. So adding that little negative 1 there in front just kind of helps you realize that there are actually 2 factors there. All right, in the next one here, we have this new rule that we haven't seen yet. I have a power raised to a power. That is exponentiation. What do we do with the 3 and the 2? We multiply, okay? So again, we come down 1 rung. If we're exponentiating, 3 raised to the 2nd power, we come down a rung to multiplication. So I'm going to go ahead and just write that as negative 3.1 to the 6th power. That's all I'm doing for that. And on that last one, I can do what we just talked about. A negative base raised to an odd power is going to be what type of number? Negative. So I'm going to go ahead and write that as negative 1 times 3.1 to the 5th. And again, this is just one way to do it. There are several different roads that lead to the Garden of Eden. All right? So that's all I did on the first line. Now I'm going to go ahead and see what I can combine on the next line. First of all, since this is just one term, we can combine all these factors in any order we want. -1 times -1 is what? +1. So I can get rid of those negatives. And now I have 3.1 to the 4th times 3.1 to the 5th. Those are the same base. So that's 3.1 to the what power? 9th, right? I add those. Okay, and now I'm left with this guy here. And I want to get the bases the same, because my base right now below is 3.1. That's -3.1. So now we just kind of use what we just talked about. It's a negative number raised to an even power. Does that become positive, or does it stay negative? It becomes positive. So that's the exact same as positive 3.1 to the 6th power. Okay? And now we can finish in our final step, because now we have the bases the same. And if that kind of looks funny to you, it looks a little funny to me, you can always add parentheses like that. Help yourself. But now the bases are exactly the same. So now that's going to be 3.1 to what power? 15th. Good. We're multiplying those bases, and so one rung lower is addition. We add those, 3.1 to the 15th. All right, so here's the rule of exponent that we just learned. Or let me do this. Let's do x to the 8th power raised to the bth power is the same as x to the what? AB, right, you multiply, okay? So that's kind of a generalization of the rule of exponent that we use. All right, so keep that in mind. Parentheses are hugely important. What am I actually raising to a power? If there's no parentheses, it's the number that is immediately to the left, right? All right, the next one here. Based on what we just did, here's your chance to try it out. I'll give you like 1 minute to do that, and then we'll kind of come back together. Careful with your grouping symbols. Parentheses are better to have and not need than to need and not have. But ultimately, when you're trying to combine things, you do have to tear down walls to bring people together or like factors together. These brackets here, it's just another parenthesis. I just use them because they're on the outside, but they could easily be parentheses as well. All right, so if you're working still, keep going. I notice kind of that I have 3 main factors in this one term. So again, as I go down, I'm going to try and do something first with each factor, okay? Inch by inch, it's a cinch. So -x to the 4th, that's the actual -x to the 4th power. Is that going to end up being a positive or a negative? Positive. Positive, right? So I could drop that negative and just call it x to the 4th, okay? One less thing to worry about. In here, you can either work from the inside out or the outside in. I like to work from the outside in, okay? But it would work either way. So what I would do is combine those first. What would we do with those? Multiply. So I'm going to keep my base the same, -x to the 6th, okay? And on the next one, I have a negative raised to an odd power. Is that going to end up being a negative or a positive? A negative, right? Odd exponents, they pair up, and there's always an odd man out, which keeps it negative. So I'm going to write that as -1 times x to the 5th, right? Like that. Okay, so now moving down on this line, I could bring the -1 out front, and I notice that I have like factors, x to the 4th times x to the 5th. That's x to the what? 9th, okay? And so all I'm left with then is this guy here, and then I just ask that question again. It's a -x raised to an even power. What's going to happen with the negative? Stay or go? It goes. So that becomes times positive x to the 6th. And now I have my bases the same, x to the something times x to the something. What do I do with the exponents? I don't even I add them. Good. So it's going to be 15. And then, of course, now you don't really need the -1 written there. You can just put a negative in front like that. Okay? Because we know what that means. That is -1 times whatever x is to the 15th power. So again, that's not the only sequence that you could use to get to that final answer. As long as you're doing things correctly, different paths lead to the Garden of Eden, all right, which is paradise. That's where we're going. All right, comments or questions on that one? Yeah.
So, like, I got the same answer, like, basically the same. Yeah, I got the same answer. But I did because I dropped the negative sign in the 6th one, because I did the 3 times 2 is 6.
And so you already had it gone right there?
Yeah.
That's fine.
And then I can
Yeah.
find the point.
That's fine. Yeah, that's fine. Yeah. That's like doing 2 things in 1 step, which is fine. I'm fine with that if I can follow your work. Here's the thing. Remember, we're focusing on the process this year. So, like, when in doubt, when in doubt, don't leave it out. When in doubt, don't leave it out. Here's what I would tell you just kind of in general. The more things that you do per step in your head, the more likely you're going to make a careless mistake, okay? So that's fine. There is merit in being quick, right? I want you to add fractions in your head, so something like that would be perfectly fine, okay? Yeah. Use them? Like have these as parentheses instead of braces or brackets? Do this? That would be actually equivalent. Yeah. That would be equivalent, but I would consider it more simplified if it has less stuff in it. And so I would think that a slightly more simplified answer would be that. Yeah, okay? But they are both equivalent because it's an odd exponent. If this were an even exponent, they would not be equivalent, okay? So yeah, like if I were making a multiple choice test, that would be my answer choice on the multiple choice test, okay? So simplifying is kind of one of those things that is not really objective. It's kind of like, it looks simple to me, and someone else, no, but you can do this. I'm not going to mess with it. Looks good, right? So just basically, if it's as small as possible or it has fewer things in it, we can consider it simplified. All right, this one here. I'm going to give you a hint. Do it on your own. I want you to write it as a power of 2. 2 to some power. There's kind of a little bit of a guideline. Write it as 2 to some power. Yeah, this might, again, I'll give you 1 minute. That's enough just to kind of get it going. Okay, I'm going to look at this now. If you're still on your way to the final answer, don't let me bother you, okay? 2 main factor groups. I see grouping symbols. I see exponentiation. So my first step would probably be to combine those. That's 2 to the what? 7th or 12th? 12, right? That's exponentiation. 1 rung lower is multiplication. This one is 4 to the 3 times 2 is 6, okay? Now from there, can I call that 2 times 4 is 8, 12 plus 6 is 18? Can I call that 8 to the 18th? I cannot do that, right? Because an exponent counts how many of that particular type of base I'm multiplying together. I have 6 4s and 12 2s. That's not the same as 18 8s, right? That's a much bigger number. So the rules of exponents only work when the bases are the same, right? And 2 and 4 are not the same. So you can't do that. But that makes a great answer choice on a multiple choice question on a test, 8 to the 18th, okay? So by giving you the hint of writing it as 2 to the nth, here's what you could do. Okay, so I got 2 to the 12th. Let me just put parentheses where the 4 is. So instead of 4 to the 6, now I have parentheses to the 6. Can I write 4 in terms of 2 as a power of 2? Yeah, it's 2 squared, right? So that's all I did. I just simply replaced 4 with 2 squared. And now I get 2 to the 12th times 2 to the 12th. And now I have the same base, so that's 2 to the 12th plus 12, which is 2 to the 24th power. Okay, so that's how you would probably do that one. Now let me kind of come over here. There's another way to do this. Can you write it as 4 to the n? Well, yeah, you could. You would still end up with 2 to the 12th times 4 to the 6th. But now you would have to somehow write 2 as a power of 4 instead of 4 as a power of 6. And it can be done, but it's not as easy. 2 is the same as 4 to what power? Louder? A half. Very good. We haven't talked about fractional exponents here, but 4 to the 1/2 is the same as 2 because, let me come over here and find some room, the square root of x is the same as x to the 1/2. The cube root of x is the same as x to the 1/3. The fourth root of x is the same as x to the 1/4, so on and so forth. Okay? So 4 to the 1/2 is the same as the square root of x. And so now you get 4 to the 1/2 times 12 is 6, and you end up with 4 to the 12th. And so those are equivalent. So it can be done. But it's easier to write it in terms of base 2. All right, last one here. We'll do this one together. You have one term. You have 3 factors in the top and 2 factors in the bottom. It looks like we have bases of 49, 9, 7, and 3. We want to write this as powers of as few bases as possible. So if you notice, look at your prime bases. 7 and 3 are prime. Can we write 49 as a power of 3 or 7? Yeah, that is 7 squared. Can we write 9 as a power of 3 or 7? Yeah, it's 3 squared. So that's 7 to the 5th, all over 7 cubed, times 3 squared. Now in this problem, you do have the option, if you were just working it on your own, those would divide out, right? 3 squared over 3 squared, that's 9 divided by 9, that's 1. Okay? But I'm going to keep them in there because I want to show you some rule of exponents, all right? Here's what we could do. Let's go ahead and combine everything in the top. 7 squared times 7 to the 5th, that's 7 to the 7th, right? Times 3 squared. And at the bottom I have 7 cubed times 3 squared. So what I've done is in the top I've collected like bases. Now, we're dividing. So here's the rule for division. A to the n divided by a to the m is equal to a to the n minus m. Good. So multiplication, we add the exponents. Division, we subtract. Numerator exponent minus denominator. So we can write this now as 7 to the 7 minus 3rd power times 3 to the 2 minus 2th power. Okay? So that becomes 7 to the 4th times 3 to the 0. Ruh-roh. What is 3 to the 0 power? 1. Anything to the 0 power other than 0 is 1. Okay? So that's just 7 to the 4th. And that would be the same thing as if you had divided out the 3 squareds up there. 9 divided by 9 is 1. 3 to the 0 is 1. So your final answer is 7 to the 4th. Okay? All right, there's about 1 minute left. We finished example 1. You notice we kind of already know the rules of exponentiation, but the way that we're reviewing them are in problems that are a little bit more worthy of your caring efforts, okay? Tomorrow we'll review all of those rules, and then we're going to meet negative exponents and fractional exponents, which we already kind of alluded to today. So remember, there's a worksheet out there. You should start practicing. The key is posted, so check your work. I'll be in the morning at 8 o'clock if y'all have any questions, all right? Until then, have a great day.